Section 4 is the compressible fluid model, and these are the two big ideas that we already saw in class today, and we'll briefly review what we did in class before we go on to finish Section 4. So part 1 was what happens while a capacitor charges, and our first experiment in that section was to add a second battery pack to an already charged capacitor. So here's the charging circuit, and then here now we're going to add a second battery pack. And what we noticed was that the bulbs lit again, and using the compass we could tell that more charge was moving to the top plate of the capacitor and more charge was leaving the bottom plate of the capacitor. This made it look like charge was compressible, that top plate was sort of already full after the first battery pack had been attached, but then when we attached the second one, we were able to put more charge on there. So this is a little bit like the way air behaves, that an area that is already full of air could actually hold more air if you compress it and push more in there. So we did an activity with the air syringes to take a look at that analogy. Review. In terms of electric pressure, explain. What we want to do here is explain the charging and why the charging stops and why it moves again when you add another battery pack in terms of this idea of electric pressure. So we developed this idea of electric pressure after looking at how air pressure was behaving and causing things to happen or not happen with the syringes. So question 1, why does charge move when a battery is initially connected to the capacitor? Well, the battery is trying to push towards the top capacitor plate, so it's pushing outward from the positive terminal, and you can think of that as electric pressure. There's electric pressure pushing on the charge in the wire. The top capacitor plate has just a normal amount of charge. It doesn't have anything really compressed there, so there's no electric pressure pushing back. So because we have more pressure pushing towards the capacitor plate than we have pushing back towards the battery, the charge will move in the direction from the positive terminal of the battery toward the top capacitor plate. So it's because of the pressure difference between the battery terminal and the top capacitor plate. Because there's a higher pressure at the battery terminal than there is at the top plate of the capacitor, it moves towards the top plate of the capacitor. 2, why does charge stop moving? Well, as more and more charge accumulates on the top plate of the capacitor, it's getting compressed. Just like when we put more air in syringe B, it got compressed and that air pressure started to push back. So as we accumulate charge here, we have increasing amounts of electrical pressure pushing back towards the battery. When that electric pressure pushing back is equal to the electric pressure of the battery pushing forward, the charge will stop moving because there's not a pressure difference anymore. Charge will only move when there's a difference in pressure. 3, why does charge move again when a second battery pack is connected? When we add a second battery pack, we are now increasing the pressure at the location of the battery. So now you have extra high pressure pushing towards the capacitor, and the capacitor is pushing back, but not as much as this new stronger battery is pushing towards it. And so because of that difference in pressure, you're going to have charge move again towards the top capacitor plate. In conclusion, how is air analogous to electric charge? Well, first of all, charge can be compressed like air. Second, air moves when there is a pressure difference. So when there's a difference in air pressure between two places, the air will move from one place to another. Charge also moves when there is an electric pressure difference between two places. And lastly, both air and charge increase pressure when they are compressed, and they will push back harder as the compression increases. Part 2, how is electric pressure influenced by a battery? We will do 3 parts here. 4.3, we will propose a model of how a battery pushes on charge. In 4.4, we'll look at how does below normal air pressure behave. And in 4.5, we'll look at, is this pressure creating model of a battery consistent with our observations? So section 4.3, So 4.3, a proposed model of how a battery pushes on charge. Suppose a battery moves charge internally like this, out of its bottom terminal and into its top terminal. The result of this would be charge compression at the top terminal and charge depletion at the bottom battery terminal. The compression produces above normal high pressure in the top terminal. The depletion produces below normal low pressure in the bottom terminal. And so we've labeled the positive terminal of the battery high pressure. We've labeled the negative terminal of the battery a low pressure region. If this proposed model is correct, then the battery would produce high pressure in wires connected to the positive terminal, and it would produce low pressure in wires connected to the negative terminal. Before we can test this model, however, we need to find out how below normal air pressure behaves. So 4.4, how does below normal air pressure behave? We're going to look at three situations with the air capacitor. In situation 1, both chambers are open to the environment. So they're going to be a normal air pressure because any air could enter or leave the open hole to adjust to regular atmospheric pressure. So the membrane is not stretched one way or the other. We have normal pressure and there is no attempt by air to move from one side to the other. So no difference in pressure, no air tries to move, and the membrane is straight. In situation 2, the right chamber is open to the environment and the atmosphere. The left chamber, air has been blown in there and the hole has been closed. So in here we have high air pressure now, and on this side normal air pressure. And you can see that the membrane is stretching this way. So the air is trying to move from high to normal. So we have a pressure difference, and we can see that air tries to move from high pressure to normal pressure. In section 3, the left chamber is open, and so we have normal air pressure in there because it's open to the environment, to the atmospheric pressure. Air has been sucked out of the right chamber though, and the hole has been closed. And so you can see here the membrane is stretching this way. Why is it stretching that way? It's stretching that way because air is trying to move from a normal air pressure to this area of low air pressure. So there's a pressure difference, and we can see the air tries to move from a region of normal air pressure to a region of lower air pressure. What are some examples in daily life where normal air pressure makes something move? In the reading this week, you will read about 2 of those. And the conclusion then is air moves when a pressure difference exists. Air movement will either move from a region of high air pressure to a region of normal air pressure, or it can also move from a region of normal air pressure to a region that has some lower air pressure. 4.5, is this pressure creating model of a battery consistent with our observations? So what we're going to do here is take a look at what we have observed for the charging of a capacitor, and then we're going to see what this pressure creating model of a battery would predict, and if it can explain and if it's consistent with what we observed. So step 1 is to label the pressures before charging. Well, we already talked about in this model, in the proposed model, the pressure of the positive terminal of the battery would be high, and the pressure of the negative terminal of the battery is low. The capacitor doesn't have anything, and no extra charge has been put on the top plate, no charge has left the bottom plate, so there's no compression or depletion yet. So both of these plates would both be at a normal electric pressure. So these are the pressures before charging, before the battery is actually connected into the complete circuit. Draw an arrow to show the observed charge flow during charging. I'm not actually going to draw it here, but you can draw it in your notes. We observed that it went clockwise around the circuit, except it did not go through the capacitor. So we could draw a continuous arrow going around like that. Now, according to the proposed model, why does the top bulb light? Well, if we look at these electric pressures, The battery is at high pressure and the top plate of the capacitor is at normal pressure. Well, according to our model, charge would flow from an area of high electric pressure to an area of normal electric pressure. So this difference in pressure here is going to cause charge flow in the direction towards the top capacitor plate. Why does the bottom bulb light? Well, if we look at the pressures here, the bottom capacitor plate is at normal pressure and the negative terminal of the battery is at low pressure. And as we just saw with the air capacitor, just as air will flow from a region of normal air pressure to a region of low air pressure, the electric charge will move from a place of normal electric pressure to a region of low electric pressure. So that means charge is going to be pushed and pulled in this direction to the left through that bottom bulb. C, why do the bulbs become dimmer over time? Well, over time, the pressure of these capacitor plates is changing. So the top plate is gaining charge and that charge is getting compressed, and so we have an increasing pressure on the top capacitor plate. As that pressure increases, there's now not as much of a difference between the battery and the top capacitor plate. As the difference gets smaller and smaller between those pressures, there's not as much push on the charge, and so the flow rate decreases. And then in D, why does charging eventually stop? Well, what's eventually going to happen is the top plate will eventually get up to the same electric pressure as the positive terminal of the battery. It will get to be a high pressure. When that has a high pressure, you now have the same push back as you have forward, and no charge is going to move. And the same thing is true of the bottom plate. Here's the pressures after charging. The bottom plate eventually, so as charge is leaving the bottom plate, the pressure is getting lower and lower and lower. Eventually, it will be the same lowness as the negative terminal of the battery. And at the point when you get to the point where there's no difference in pressure, the charge is not going to move, because remember, it's the difference in electric pressure that causes the movement. Part 3, how can we visualize electric pressures in a circuit? So we're going to do some color coding to show the electric pressures in each wire and at the battery terminals and on the capacitor plates. And you received a handout in class that has this information on it and also has the reading for section for 4.7. So this is what the color coding is. Red is going to represent highest pressure above normal. The positive terminal of the battery will always be red, and the negative terminal of the battery will always be blue. It's going to be the lowest, below normal. Yellow will represent normal pressure. So when you're charging a capacitor, the capacitor plates will start out yellow because they're starting out at a normal electric pressure. And at this point, you're now ready to finish reading that handout that has these color codes on it, and then proceed with the homework.